So good evening, all of you.
Good evening, sir.
Good evening.
Good
Good
evening,
evening.
sir.
Good evening.
Good evening. Good evening. So now we will start with new topic, and that is thermal physics. So we will talk about mainly the thermal properties of especially gases. And you know that in thermal physics we study assembly of large number of atoms. System has large number of atoms, and because of that large number of atoms we can find the macroscopic properties using in a statistical fashion. And this thermal physics has evolved in various stages. So initially it was not known that matter is made up of atoms or molecule. So before that thermodynamics was developed. So that is known as classical thermodynamics, where we talk about only macroscopic properties. But later, when it is known that matter is made up of atoms and molecules, then another approach develops. So that was one was the kinetic theory of gases, which uses the probability distribution, and another approach was statistical mechanics, where we talk about the microscopic state of the system, and then we use the statistical method to find the thermal properties. So thermal physics has evolved in three stages. One is thermodynamics, then you have kinetic theory of gases, and then statistical mechanics. Is it clear? So let's see. You should write down these points that, as I have already told you, that the thermal physics, this subject involves studying assemblies of large number of atoms. And you will see number of atoms of the order of 10 to power 23. We will discuss the concept of mole. So in 1 mole, approximately 10 to power 23 atoms are there. So if you have such large number of atoms, then we can use the in this macroscopic system, which allows to treat some of their properties in statistical fashion. Because of the large number only, you can use the properties in statistical fashion. So I have already told you that this thermal physics has evolved in various stages, and that has left with us three approach to the subject. So these are the three approach to the thermal physics. One is the classical thermodynamics, another is the kinetic theory of gases, and third one is the statistical mechanics. Is it clear? So please note these points. And I will also share you the PDF file for at least for a preliminary part, the basic concepts that I will discuss in introductory lecture, because first lecture is always a introductory lecture. I will just introduce the subject, and we will discuss the some basic definition and concepts that we are going to discuss throughout your thermal physics. So first lecture is introductory lecture, and I have prepared a PDF file for the this introductory lecture. I will share you in your WhatsApp group. Okay? So you should note it down, and we will share it also. You will get in detail. Clear? So please note down. Okay? Is it clear?
Yes, sir.
Now see what we do in thermodynamics. So in classical thermodynamics, it deals with the macroscopic properties, means bulk property of the system, such as pressure, volume, temperature. These are the bulk property. So we call it as a macroscopic properties, without worrying about the underlying microscopic physics. We are not concerned about the microscopic physics or microscopic constituent of the system. So it deals with the macroscopic properties without underlying the microscopic physics. Now it applies to a systems which are sufficiently large that microscopic fluctuation can be ignored. You will see, we will talk about thermodynamic limit when number of particles is very large. So microscopic fluctuations can be ignored, and on an average, you will see the bulk property will remain constant, especially you will say pressure. So that's why it applies to a system which are sufficiently large that microscopic fluctuations can be ignored, and it does not assume that there is an underlying atomic structure to matter. So this is the classic thermodynamics approach. Is it clear?
Yes, sir.
Yes, sir.
So please note it down. ठीक है?
Yes, sir.
Now see, what in the kinetic theory of gases, we tries to determine the properties of gases by considering probability distributions associated with the motions of individual molecules. We will focus on the microscopic nature of the matter, and we will talk about the probability distributions associated with the motion of the individual molecules, and then we will see the properties of gases. So that is the kinetic theory approach, where we focus on the probability distribution of individual molecules. Clear? ठीक है? What we will do in kinetic theory of gases?
Sir, can you please show the previous slide once?
Okay. I will share you in detail. Everything will be written in PDF file, because introductory part I will share you. So don't worry.
Okay, sir.
Okay. Now third is the statistical mechanics approach. Again, we try to describe the individual microscopic state of the system. We will talk about the microscopic state of the system, and then we will use the statistical methods to derive the macroscopic properties of the system. So thermal physics we can study in these three approach: classical thermodynamics, kinetic theory, and statistical mechanics. Classical thermodynamics was developed even before kinetic theory of gases. As I have already told you, that when it was developed, it was not known that matter is made up of atoms or molecules. So that's why first classical thermodynamics was developed, then kinetic theory came, and finally this approach comes into existence. Is it clear? What is
Yes,
the
sir.
thermal physics? What you study in thermal physics? So I will discuss two parts: classical thermodynamics and kinetic theory part. Statistical mechanics part will be discussed by Sandeep sir. Okay? So I will discuss the syllabus of first two parts, and then third part will be discussed by Sandeep sir. Clear? Now see, first we have to see the syllabus.
सर
Yes.
excuse me सर सर फिर से आप फर्स्ट और सेकंड स्लाइड दिखा सकते हैं
Second slide.
सर फर्स्ट भी
Okay.
तो
Just
थोड़ा
check.
साइड हो सकते हैं
ठीक है?
ओके सर सेकंड भी एक बार दिखा दीजिए
ये सेकंड ही है, नेक्स्ट वन.
ओके
Clear?
Yes, sir. Yes, sir.
Okay. Now, first thing is you should know the syllabus. So first we will talk about what are the preliminaries required for this to study. Means we want some basic concepts and definitions. What are the basic concepts and definitions that we are going to use? So this is the introduction part, and in today's lecture I will just focus on the basic concepts and definition. So what point you should know? You must know what is a mole. What is a mole? Then you must know what is the thermodynamic limit. What do you mean by thermodynamic limit? Then we will also distinguish between extensive and intensive properties. Extensive and intensive properties. Extensive and intensive parameters, you can say. So throughout thermal physics, whenever new parameter will come, you have to see whether it is extensive or intensive. So if you know the meaning of extensive and intensive, only then you can identify. Sometimes they have also asked that this particular parameter is extensive parameter or intensive parameter. So it's a basic part you must know. Then you will see mostly we will talk about ideal gases, and finally we will talk about the real gases. So most of the study is based on the ideal gas. So you must know what is an ideal gas and when you will say a gas is an ideal gas. Yes or no? What is the assumptions on ideal gas and how it is different than the real gas? Is it clear?
Yes, sir.
So then we will talk about what is the definition of heat. Definition of heat. Then we will talk about heat capacity. We will define heat capacity of an object or matter. We will talk about thermal equilibrium, temperature what is and thermal equilibrium. Thermal equilibrium. And in this, we will also talk about zeroth law of thermodynamics. Zeroth law of thermodynamics.
Hello.
Yes?
So, match done.
Please mute your voice.
Okay. कोई प्रॉब्लम आई?
Please mute your voice. ठीक है? And we will just introduce about the Boltzmann distribution. You will study the derivation of Boltzmann distribution. You will study in statistical mechanics because we have to use the Boltzmann distribution. So I will just explain you what is the Boltzmann distribution and that you will see what is the Boltzmann factor. Boltzmann factor. Okay. So this is the first part. Preliminaries that you are required. What are the basic concept and definition? So that we will discuss. Is it clear?
Yes, sir. Yes, sir.
So please note it down. I will share you the PDF file for this particular part so that you will get in detail everything. I will explain it here, but you will get its PDF file also. So can I take next part?
Yes, sir. Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Next is we will focus on I will first focus on kinetic theory of gases and then we will see thermodynamics part. So second is kinetic theory of gases. Kinetic theory of gases. So we will see what are the basic assumptions of kinetic theory of gases. You must know what is the basic assumptions. On what assumptions this kinetic theory is based? Then we will calculate pressure exerted by an ideal gas. Pressure exerted by an ideal gas. We will calculate pressure exerted by an ideal gas. And in this, we will see kinetic interpretation of temperature. Kinetic interpretation of temperature. We will see RMS speed. We will talk about average RMS and most probable speed. So we have mainly average RMS and most probable speed. Most probable speed. Then we will also see we can derive the ideal gas equation from the kinetic theory of gases. So elementary deductions of ideal gas laws. Ideal gas laws. Ideal gas law, elementary deductions can be done for ideal gas law. Then we will also talk about, you will see, we will talk about heat capacities in ideal gas, in a kinetic theory of gases. Using this model, we can find the heat capacity. So we will discuss the classical theory of heat capacities of gases. heat capacities of gases. And again, we will introduce the concept of degree of freedom. We need concept of degree of freedom to define the heat capacity, and we will also talk about principle of equipartition of energy. Equipartition of energy. Principle of equipartition of energy. Then we will see Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution. So we will see velocity distribution and speed distribution. Velocity distribution and speed distribution. Velocity distribution and speed distribution. Then we will talk about molecular effusion. Molecular effusion. Molecular effusion. So we will see molecular distribution, molecular distribution, and then we will talk about flux and effusion. What is molecular flux and effusion? Okay. Next point will be, we will talk about mean free path and collisions. What is mean free path and collisions? Mean free path and collisions. And we will also, using the kinetic theory of gases, we will introduce the transport properties in gases also. We will use the properties. So transport properties in gases. And here we will talk about viscosity, then you have thermal conductivity, and we will discuss the diffusion also. Okay? So using kinetic theory of gases, we will discuss these points. Please note down. Okay?
Yes, sir.
Please note it down. So can I take next slide?
Yes, sir.
Yes, sir.
So now third part is the thermodynamics part. So in this, we will talk about first law of thermodynamics. The first law of thermodynamics. First law of thermodynamics. Again, we will discuss here energy and heat capacities. Energy and heat capacities. Then we have the second law of thermodynamics. Law of second law of thermodynamics. We will talk about heat engines and concept of entropy. We will introduce the concept of entropy. Then we will talk about thermodynamic potentials. Potentials. Thermodynamic potentials. And then we have the third law of thermodynamics. Third law of thermodynamics. Clear? Now, till now, we will talk about only ideal gases, but you know that real gases are different than ideal gases. They are in idealized situation. So if you have to talk about real gases, then we have to change the ideal gas equation. So what we will do, we will talk about real gases. We will introduce the real gases now. So finally, now we will talk about real gases. So we will see how deviation from perfect gas behavior. Deviation from perfect gas. Deviation from perfect gas behavior. And the most important one is the van der Waals gas. So we will talk about the van der Waals gas. The van der Waals gas. We will derive the equation of van der Waals gas. There are some other equations also. One of them is, we call it as Dietrich equation. T-E-R-I-C-I. So we will also talk about Dietrich's equation. Then we will talk about virial expansion. Virial expansion. And we will discuss the reduced equation of state. Equation of state. Then we will introduce the chemical potential. We will talk about the chemical potential. Then we have cooling of real gases, and we will also talk about phase transitions. Phase transitions. ठीक है? So we have to focus on these topics. So that will be the part of kinetic theory and thermodynamics part. Is it clear?
Yes,
sir.
Sir, which book to follow?
It's Blundell. I have taken reference from this particular book, Blundell. ठीक है? Have you noted these points?
Yes, sir.
Chalo. So now we have to start with so first point is mole. What is a mole? So you all know what is a mole? So it is equal to the Avogadro's number. So it is defined as the quantity of matter that contains as many number of atoms as the 12 gram of carbon contains. Means what is the number of atoms in a 12 gram of carbon? That number has defined as mole, and that is equal to the Avogadro's number, 6.022 10 to power 23. So 1 mole is 6.022 10 to power 23. And for all matter, if I say 1 mole of carbon, 1 mole of water, 1 mole of benzene, so all contains the same number, that is Avogadro number. Clear? So you can write a mole is defined as the quantity of matter that contains as many number of atoms or molecules as the number of atoms in exactly 12 gram of carbon 12. So 12 gram, or this will be what? In kg, 0.012 kg. So that this is the definition. So a mole of atom is equal to Avogadro number. number Na, and this is 6.022 10 to power 23 of atoms. Yes or no?
Yes, sir.
So whether you have 1 gram of water, 1 mole of water, 1 mole of carbon, 1 mole of, let's say, sodium chloride, 1 mole of benzene, all contains the same number, and that is 6.022 10 to power 23. So even 1 mole is very large number. 6.022 10 to power 23. ठीक है? So if M is a mass of one atom, then molar mass, what? Let's say molar mass is capital M, mass of 1 mole. This will be given by what? M into Na. This will be the molar mass. Yes or no?
Yes, sir.
Yes, sir.
So, and if molar mass is given and you have to find mass of one molecule, this will be M by Na. So, what is molar mass of carbon 12? Molar mass of this will be what? 12 gram or 0.012 kilogram. What is the molar mass of H2O? H2O, this will be 18 gram or 0.012 kg. ठीक है? So you know the molar mass, and then if you divide it by Avogadro number, you will get mass of one particular atom or molecule, whether it is H2O or carbon. ठीक है? Is it clear?
Yes, sir.
So you know about mole. Now next is, what do you mean by thermodynamic limit?
Sir, can
Why?
you show previous slide?
Yes, yes.
Okay, sir.
Okay. So now we have to talk about thermodynamic limit. So when you have very large number of atoms or molecules of the order of 6 into 10 to power 23, then you can see this, if you calculate the pressure exerted by these molecules on one particular surface of a cubical box, that will be almost constant if number is very high. Thermodynamic limit means when number tends to infinity, but when number is very large, then there will be variation in pressure. So that's why we consider the large number, so that there is no fluctuation in pressure. Pressure is almost constant. So that limit is n tends to infinity, means number is infinitely high. So let's see. I'm showing you this particular PDF file so that you can easily understand. I will share you this file itself. Just see. Now see. What is the thermodynamic limit? Can you see it?
Yes, sir. Yes, sir.
So the large number of molecules in a, no need to write because I will share it. Just try to understand what do you mean by the thermodynamic limit. Large number of molecules in a typical thermodynamic system means it is possible to deal with average quantity. If number is very large, then you can deal with average quantity, and you will see with respect to that average, fluctuation of any parameter is almost zero. And in the limit n tends to infinity, if number are infinitely high, that fluctuation is almost zero. So that's why in thermodynamics we talk about thermodynamic limit. So our system is what? Let's say you have confined 1 mole of a gas in a cubical container. So there are 10 to the power 23 number of molecules, and they are colliding with each other and also with the walls of the container. And because of that collision, they will transfer momentum, or they will have impulse on a particular wall. So you have a rate of change of momentum, that is force, and if you calculate force per unit area, that will be pressure. And in the limit n tends to infinity, that pressure is almost constant. So if you want to understand this concept, I am taking one analogy. Let's assume you are inside a small hut and that has a flat roof. Roof is flat and rain drops are falling on the hut. So what will happen? Just see, if hut is very small, few raindrops will strike on the surface of the roof. Yes or no? When I'm assuming roof is very small, so occasionally raindrop will collide with the surface of the roof. Yes or no? And what will happen? When they will collide, they will transfer momentum, or they have impulse. There will be rate of change of momentum. So that's why I am representing here force exerted by the raindrop with time. So in this time interval, no raindrop have arrived. But at this particular time, let's say one raindrop has arrived here. So there will be transfer of momentum, and that is equal to impulse F into T. Then again, no raindrop, but you are getting force at this particular time. Then let's say 2 or 3 more raindrops comes. So you will get this particular situation, force, and so on. So this is the case when this roof is very small. So this will be the situation. Now you can see, if you calculate the average force, then fluctuation will be very large, because sometimes it is 0 and sometimes you are getting constant value. So this fluctuation will be very large in this particular situation. Yes or no? Here I am taking raindrop that is colliding over a small roof. Yes or no? Flat roof.
Yes, sir.
Is it clear?
Yes,
Now
sir.
see what
सर
will
फिर से
happen.
समझा दीजिए एक्सक्यूज मी सर
देखो, मैं
फिर से
ये कह-
समझा दीजिए
देखो हमारा केस क्या है. What we have to study, you have a large number of molecules in a gaseous container, and they are colliding with the walls. They are colliding with each other and also with the walls, and you will see that we will get a constant pressure. So why we are getting constant pressure? Because of the very large number of molecules. So that we call it as in the thermodynamic limit, you will get the constant pressure. अब इसको समझने के लिए हमें क्या करना है, एक एनालॉजी लेते हैं कि अगर एक कोई हट है जिसका जो रूफ है वो बहुत फ्लैट है और साइज बहुत छोटा है, इट्स अ स्मॉल साइज, क्लियर, एंड रेन ड्रॉप्स आर फॉलिंग ऑन इट. तो क्या होगा अगर साइज बहुत छोटा है? So let's say one roof at a particular time, one raindrop will strike it and it will transfer the momentum. Then let's say in this time interval, no raindrop has fallen on it. Then another raindrop strikes. Then let's say 3 raindrops strikes. Then no raindrop strikes. So what will be the force exerted by the raindrop? You will get this type of situation, force versus time. है कि नहीं? So means in this case, if you see the average force and the there is a fluctuation, there will be large fluctuation in average force. क्योंकि इनका average लोगे, so average and this value, there will be slight variation. They will not be constant. कभी 0 हो रहा है, कभी constant 0. So there will be, if you take average, then this, there will be, and the fluctuation, they have large difference in fluctuation and the average value of force. Yes or no?
Yes, sir.
Now see, अब हम क्या करते हैं? Let's increase the size of the roof. हमने 1000 times increase कर दिया. Now area is 1000 times. अभी same rain drop strike कर रहे हैं. So what will happen when area is very large? So what will happen? Now at each time there is possibility that raindrop will strike and more raindrop will strike on the surface. है कि नहीं?
Yes.
अगर एरिया बहुत ज्यादा कर दिया. So means
Sir,
at
probability
each
increase
time,
होगा.
yes, probability of collision means more number of raindrops will collide. So that's why what has happened? Force, this magnitude of force has also increased. And just see, if you see this fluctuation, there is a fluctuation, but average value has increased. So if you see the fluctuation with respect to average value, that fluctuation is small. Yes or no? मतलब जैसे जैसे आप एरिया इंक्रीज कर रहे हो, जो फोर्स का फ्लक्चुएशन है, वो क्या हो रहा है? एवरेज वैल्यू से थोड़ा डिक्रीज कर रहा है. अभी फ्लक्चुएशन कम हो रहा है विथ रिस्पेक्ट टू एवरेज वैल्यू. यस और नो?
सर एवरेज वैल्यू भी इंक्रीज होगा फिर.
हाँ, एवरेज वैल्यू भी इंक्रीज हो रहा है. यस, एवरेज वैल्यू इज ऑल्सो इंक्रीजिंग. इफ यू आर इंक्रीजिंग द एरिया, एवरेज फोर्स इज इंक्रीजिंग ना. वहां तो देखो जीरो भी था, जीरो बहुत समय जीरो था, देन यू विल गेट सम फोर्स. सो जस्ट सी, एवरेज वैल्यू इज इंक्रीजिंग. If you are increasing the area, average value is increasing. And this magnitude of force is also increasing because more number of raindrop is colliding. Yes or no?
Yes sir, got it.
Yes, sir.
अब देखो, अगर हम इससे भी 100 times या 1000 times if we increase it, अब क्या होगा? You have this type of situation. Fluctuation and average value is almost same. Yes or no? I have further increased the area. Is it clear? Now you can see fluctuations are smoothed out. It is almost equal to the average value. It means in this case, if you keep on increasing the area, more and more raindrop will fall on the roof and fluctuations will be smoothed out, and that will be equal to the almost average value. Yes or no?
Yes sir.
Yes, sir.
The second case, the fluctuation is smaller.
Is
than
it clear?
Yes, sir.
So now this is the case of force. But just see, if you are increasing the area, force is increasing. So if you calculate the pressure, pressure is what? Force per unit area. This value will be almost constant. This will not change because as area is increasing, force is also increasing. So if you calculate the pressure, pressure will be almost a constant value. Yes or no?
Yes sir. Yes sir.
So finally, just see, these 2 points are important. Notice 2 key things about these graphs. One thing is the force on average gets bigger as the area of roof gets bigger. If area of the roof is increasing, what will happen? The force gets bigger as the area of roof gets bigger. And this is not surprising because the bigger roof catches more raindrop. When more raindrops are striking on the surface, what will happen? Force will increase and average force will also increase.
Yes, sir.
And second point is the fluctuations in the force gets smoothed out and the force looks like it stays much closer to its average value. ठीक है? So that's why fluctuations this almost equal to the average value. Now the force grows with area, so it is useful to consider the pressure. Pressure is what? force per unit area. And you will see the average pressure due to falling raindrop will not change as the area increases. But the fluctuation in the pressure will decrease. If you see about pressure, you will see the average value. This will decrease in case of if you are calculating the force per unit area. Okay, so at least pressure will remain constant. It will not vary if you are increasing the area. So in fact, we can completely ignore the fluctuations in the pressure in the limit that area of the roof grows to infinity. If you are assuming that roof area is infinity, then pressure will be constant. And this is what we call it as a thermodynamic limit. Okay? Is it clear?
Yes, sir.
Yes, sir.
Now I am taking analogy with this example, but our case is what? Area of the container on one side is fixed, but if number of molecules is increasing, and in the limit if molecule tends to infinity, you have similar effect. So that is the thermodynamic limit. In our case, if you take number of molecules tends to infinity, means very large, not infinity, it's very large. So ideal situation we say that it's a infinity. So when the number of molecule is even if of the order of 10 to power 23, that will be our thermodynamic limit. So we are dealing everything in our thermodynamic limit. So whenever we will say in thermodynamic limit, it means number of molecules is very large, of the order of 10 to power 23 or more than that. Is it clear?
Yes, sir.
So you know about mole and you know about thermodynamic limit, and why we are taking the thermodynamic limit, because when number is very large, pressure is almost constant. It will not vary. Okay? Clear?
Yes, sir.
So I will share this file, so no need to write, because these are preliminary things. Everything you will get in written form. Same file I will share you. Okay? Chalo. Now we have to see how we will identify which parameter is extensive parameter and which parameter is intensive parameter. Just give me 1 minute. So now we have extensive and intensive parameter. And intensive parameter. So let us consider a gas is confined in a container. Gas is confined here. You have large number of atoms in this. And let's say their pressure is what? Its pressure is P, volume is V, temperature is T. And I am assuming total energy, assume energy is only kinetic energy. Kinetic energy of all molecules. U is, I am considering only kinetic energy of all molecules. So U is, I am taking total energy, and that is the kinetic energy of all molecules. Now, if you have to see which one is intensive, which one is extensive, let's divide this box by this imaginary surface. Consider this is an imaginary surface and you have divided it into two equal parts. Is it clear? And just see now what will be for this particular part, what will be its pressure?
Sir, P.
So pressure is P. What will be its temperature of this particular part?
Oh, T.
T. Temperature will not change. What will be volume?
Half of.
Half
V
of
by
T.
Yes. And what will be internal energy or this kinetic energy of all molecule? That is the internal energy I am taking. This will be U by 2.
Yes, sir.
So just see the parameter which scales by dimension means if you are reducing the dimension, it is decreasing. If you are increasing the dimension, it is increasing. Those parameters are called as extensive parameter. This is called as extensive parameter. Okay? This is called as extensive parameter, and those does not change is called intensive parameter. Intensive parameter. Is it clear? So in this way, whatever parameter you required, you have to ask yourself whether it is intensive or extensive. So you have to do this experiment. Divide mentally with an imaginary surface and see whether they are changing or not. If they are changing, they are extensive parameter. If they are not changing, that is intensive parameter. Is it clear?
Yes, sir.
Sir,
Yes.
So please note down.
So intensive parameter means it is independent of amount of matter.
No, it is independent of the dimension of this box. So also number of if number of atoms are increasing or decreasing, because that is in equilibrium. Yes, because number is very high now. That's why I'm telling you, even if you divide it, that pressure will be same and temperature will not change. Temperature is when they are in equilibrium, temperature will remain same. Only thing is volume becomes half, but internal energy becomes half.
So, but entropy is extensive parameter, right?
So I will discuss those parameters. Just see the definition part first, because you know pressure, volume, temperature, energy. So I have just taken these examples. When we will talk about entropy and other parameters also, so we will discuss which one is intensive and which one is extensive. Is it clear?
Yes, sir, clear, sir.
So because I have just talked about PVTU, that's why I am taking this example. Others we will take one by one.
sir,
Huh.
sir, kinetic energy, sir, how it will vary, sir? Because temperature is same for both.
No, that depends kinetic energy of each molecule. So when number of you are adding the total kinetic energy. So when number of molecules becomes half, kinetic energy becomes half. Sum of the total kinetic energy of all molecules. So when you divide it by half, kinetic energy is changing. Total kinetic energy becomes half of that case. Yes or no?
The mass becoming half.
Yes, number of molecules become half, mass becomes half.
Okay.
Number becomes half. So, and kinetic energy is sum of kinetic energy of individual molecules. So when number becomes half, kinetic energy becomes half. Okay?
Okay, sir.
Now we will talk about what is an ideal gas. What is an ideal gas? And what is the equation of state for an ideal gas? So when you will say the gas is an ideal. What is the point? So we have to assume that there are no intermolecular forces. Assume there are no intermolecular forces. Intermolecular forces, so that molecules are not attracted to each other. So we are ignoring the molecules are not attracted to each other. So we are ignoring the intermolecular forces. In real case, there is intermolecular force. So why it is ideal? Because we are ignoring the intermolecular forces, and we are also ignoring the assume that molecules are point like. That is, have zero size. This is the idealized situation. Practically, atom and molecules have size. But when we say ideal case, so we are assuming these points. Okay? We are also considering gas molecules are moving non-relativistically. Gas molecules are moving we are assuming non-relativistic motion. So in real case, they may move with relativistic velocity also. Okay? And we are also considering temperature is very high and density is very low. Assume temperature is high and density is low. So we are assuming that temperature is not low so that gas becomes liquefied. So it is above liquefaction point. So I am considering those temperature and density is very low. But if temperature is very low, density is low, then it may liquefy or solidify also. So we are ignoring all those things. That's why we are saying that our gas is an ideal gas. Yes or no?
Yes, sir.
Yes, sir.
So if you are considering an ideal gas, then you will see we can write the Boyle's law. What is Boyle's law? You will see pressure of a gas at a fixed temperature, pressure of a gas is inversely proportional to volume at T is equal to constant. This is called as Boyle's law, that pressure of a given mass of a gas is inversely proportional to volume at a fixed temperature. Now, this is the, if you plot P versus V, you are getting this type of curve. And let's say this is at temperature T1, this is at temperature T2. So what will be relation between T1 and T2?
Even greater than T2.
Yes, T1 is greater than T2. So this is according to Boyle's law. If you have an ideal gas, so according to Boyle's law, you will get this particular relation between pressure and volume at different temperature. Clear?
Yes, sir.
Note कर लिया?
Yes, sir.
Now next is what we call it as a Charles law. Charles
Sir.
law. हाँ,
The previous
बोलो.
slide is
अच्छा ठीक.
okay, sir. Thank you.
So according to Charles law, at constant pressure, volume is proportional to T when P is constant. And if you plot V versus T at different pressure, let's say you are getting this one is at pressure P1 and this one is at pressure P2. So two different pressure I am showing. One is at constant P1, another is at constant P2. So what is relation between P1 and P2? Can you say? At a fixed wall temperature, if you increase pressure, what will happen? Yes, what is the relation between P1 and P2?
P1 greater than P2.
No, at a constant temperature, if you increase pressure,
Volume
so
of
P2
volume
is
of P1 is
P2
greater.
greater than P2.
P2 is greater than P1. Yes. Then another law is called as Gay-Lussac's law. And this will give you pressure is proportional to temperature at constant B. And in this case also, if you plot P versus T, so you have V1 volume and V2 volume. So again, V2 is greater than V1. So if we combine these three laws, we can write that PV is proportional to T. And we can write PV is equal to NKBT. N is the number of atoms. N is the total number of molecule. N is total number of molecules in an ideal gas. Or this, and Kb is Boltzmann constant. Kb is called as Boltzmann constant. Kb is Boltzmann constant. So this equation can also be written as P is equal to small n kBt. Where n is number density. N is capital N by V. Now, this equation can also be written as PVN. Kb is given by R is gas constant. R by Na. Na is the Avogadro number. Where Boltzmann constant is given by R by Na. Na is the Avogadro number. And N by number of moles. Number of moles. Number of moles is mu. Let's see, number of moles is mu is given by N by Na. number of moles is, so total mass by total weight by atomic weight. This is also equal to total weight by atomic weight. So mu is the number of moles. So you can also write this as mu RT, where mu is the number of moles and R is the gas constant. Okay, so you have to remember the ideal gas equation, whether in this form or this form. We will, throughout this analysis, we will use this equation of a state for an ideal gas, and we will also modify this equation for real gases. Is it clear?
Yes, sir.
Yes, sir.
So in today's lecture, I have just introduced, I think 2-3 points only. So in next lecture, again, I will take the other points and then we will move on to the kinetic theory part. Okay? So today I will share.
So fourth slide खोल लीजिए सर.
Which one?
Fourth sir, जिसमें आपने कुछ तो
अच्छा,
लिखवाया
ठीक
था.
है।
सर इससे आगे वाली.
इससे आगे?
यस सर. नहीं आई.
ये
नहीं
वाला
आई
या
सर.
इससे आगे?
इससे आगे वाला सर.
हाँ.
Yes, this one only.
So in today's lecture, I have just covered this part. Now in next class, I will cover it, these topics, and then we will start with kinetic theory of gases. Okay? So
Sir,
I
can
will
you show please last slide?
last slide. Yes.
सर इसमें एक डाउट है.
Hmm.
The slope of the line P1 is greater than P2 in Charles' law, also in Gay-Lussac's law. Shouldn't P1 be greater? And
No, just see. Yes, if you are taking same temperature, now let's see what will be the condition. If temperature is not changing on a given temperature, if you increase the pressure, volume will increase or decrease?
Decrease.
Yes?
Increase.
Decrease, no?
Hmm.
Decrease. If you increase the pressure, then volume will decrease. So that's why this is the P2 and P2 is greater than P1. Yes or no?
Okay, sir.
Okay? In same way, you can see here also at a fixed temperature, if you are increasing the pressure, volume will decrease. If you are decreasing the pressure, volume will increase. Clear?
Okay, sir.
So I think time is
Yes,
over.
sir.
So in next lecture also, I will take the preliminary part, and then after that, we will start with kinetic theory of gases. Clear?
Okay, sir.
Yes, sir.
Okay. So I will share this. I will share this PDF file. You can go through it. Chalo. Okay. Thank you, everyone.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.